Hi, this is video number 6 of this little series on the second special orthogonal group SO2 and the second orthogonal group O2. And in the last video we finished discussing SO2, and we want to now expand the discussion and talk about O2, of which SO2 is a subgroup. And what's being added here is a new type of transformation, and that's what's called a reflection. Now let me remind you, using my little plane here, so reminder, I'm using purple now, by the way, and it could be in honor of moving on from SO2 to O2, but it's really just because my black is running out. So reminder, I told you at the beginning that this O2 is the group of distance preserving transformations of the plane that also preserve a fixed point. And so the picture I was showing you is, so here's the plane and here's the fixed point. And I told you there's two types of transformations that make up this O2. One is the rotations, and we talked about those in detail with SO2. Rotations that fix this point. The other, though, is reflections. And I'll say more about reflections now, of course. That's what this video is about. But the way I represent a reflection with this little physical piece of paper is I just flipped it over. So the idea is this arrow goes up to where that arrow was, and vice versa. And you could reflect across a different line. So say you have this line here, and so you reflect it that way. And the point is that you are preserving this fixed point. This point here doesn't change. Now, before I get into the details, I'll make a couple of remarks. And that is that, and this is kind of maybe tying up some details that we didn't really talk about before. So one is that we talked about dihedral groups. And in particular, we talked about the dihedral group of the square, D8. We call it D8. And so this, so let me not get ahead of myself here. Dihedral groups also had rotations, can't spell here, rotations and reflections. And we called the rotations R, and we called the reflection S. And depending on which polygon you were transforming, for instance, we did D8. So this was where we're transforming a square. And so in this case, we had rotation by 90 degrees, and then we had rotation by 180 degrees, and then, by 270 degrees, and then you're back to where you started. And of course, there's the identity rotation too, which doesn't do anything. And then we had the reflection, and we chose one particular axis to reflect across, which I think was the vertical one that went this way. I don't remember for sure. But, so O2 rather, so O2 is kind of like an infinite dihedral group. And the way you can think of it is like this. You start out with the triangle, and the group of transformations of that was D6. and then you have the square. And this was D8. You could do a pentagon if I can draw one. This would give you D10, hexagon, and so on. But you see these are kind of getting closer and closer to a circle in the sense that if I took, and that's a terrible circle, but if I allow the number of edges to approach infinity, then you could think of this as sort of D times 2 infinity or something. Because this was, you know, the number of edges here was 3, and so you get D6, D8, D10. That's silly. But anyway, you get the point. It's like a infinite dihedral group. It has rotations and reflections, just like the dihedral groups do. So that's a kind of a good way of thinking about O2 to relate it to something you've already seen in the notes. And of course, we talked about this on one of the other videos as well. Now let me take off this just so I can fit another remark on here. There's some similarity. So this fixing, this business about a fixed point, the idea that you can't, that you're not allowed to move this point. Some of you are interested in theoretical physics, so I'll just say this, and the rest of you can ignore it. But so O2 is to the entire group of distance preserving transformations of R2. So O2, the orthogonal group, compares to the entire group of distance-preserving transformations of R2, which also includes translations, by the way, because I could take this plane and I could just move it somewhere. And O2 tells you you can't do that. You're ruling those out. So O2 is to that entire group, which also includes the translations, as the Lorentz group in relativity is to the Poincaré group. So this is in the context of relativity and also quantum field theory and various other physical settings where you have a particular direction associated with your group, which in this case corresponds to time. But I won't say anything more about that now. I just wanted to point that out, that the difference between allowing translation to this thing as well as rotations and reflections is the same sort of idea as you get where you're allowing the whole Lorentz, well, the restricting to the Lorentz group versus allowing the whole Poincaré group, which allows translations as well in the context of space-time. And that's all I will say about that here. Okay, so those are just some preliminary remarks about the orthogonal group. And now I want to become very concrete and just show you a specific matrix which belongs to the orthogonal group and not to the special orthogonal group. And this is a reflection matrix. So this is an example of, just to be neat, let me write it this way. So I'll say example, colon, and then I'll say a matrix that's in O2, but not in SO2, and I'll leave out the in, just so I don't have to use another line here. And that's this reflection matrix. And I'll choose a particular one here and we'll see what it does. 0, 1, 1, 0. Okay, so why am I calling this a reflection matrix? So let's test what this does to column vectors. Test its action on column vectors. And here I'm going to use a general column vector AB because it's easy enough to see even with a general column vector exactly what's happening. So I'm going to draw here XY plane. I'm going to draw a vector, column vector here. And this is the vector AB. And so that means that distance there is A. And that distance there is B. And we're going to see what it does. So we're going to take 0, 1, 1, 0. Apply this to AB. And watch what happens. Well, the first row, pair it with this column, and that picks out the B. See, the 1 goes down there and grabs the B. The 1, 0, the 1 picks out the A, and so we have BA. See, it flipped. It reversed these two entries. It took the A and turned it into a B, and a B and turned it into an A. Now you can see that I chose my vector here poorly because A is only a little bit larger than B. So if I drew what this looked like here, it would look just kind of like that, and it wouldn't be all that impressive. So let me draw another vector that's a little bit more illustrative here. So here's my x-axis, here's my y-axis. Let me draw a vector that looks like this. So here's a right angle. That distance is A. That distance is B. Now this matrix interchanges these two. It moves A to be the y component now and B to be the x component. So if B is the x component, that's this little component here, and so it goes like that. And so now this is I could draw a right angle here. That's B for this vector, and then this distance here is A. So what did it do? Well, the useful way to think about this is think about drawing this line here, and this line is y equals x. And then this line continues in the opposite direction. And the idea is that you reflected across that line. So you think of this line as a mirror. You imagine this line as a mirror, and you see this vector in the mirror, and this is the image of that vector in the mirror. It reflected across that line, y equals x. So this was kind of messy. Let me fix that. That's what this line is. It's the line y equals x. It reflected across this line. Now, I think it's pretty clear that this matrix will do that same thing to any vector because I haven't specified what the vector is. I've just said an A and a B. I mean, suppose that I pick another vector. Say I pick a vector that looks like that, for instance. So here, the x component, let me call this here big A. So this is the column vector now, big A, big B, where big A and big B are, in general, totally unrelated to what little a and little b are. In this case, here's the big B. Well, what's it going to do with this vector here? What's that matrix going to do? It's going to interchange them. So now, instead of the x component being big A, now the y component is going to be big A. So that's going to go up to about here. And then the x component, instead of the y component being B, now the x component is going to be B. So that's going to send, I have to extend it this way and scribble over what I've done over here. But that's going to send it over to something like this. And you can see once again that that's a reflection. It's reflected that vector here across this same line here, y equals x. So that's what the reflection matrix does. Now, there are plenty of other reflection matrices, and you don't have to reflect across this line. You could reflect across any other line. You can probably begin to imagine, you remember with the dihedral groups, how we could choose a particular line to reflect across, and we could get any other reflection by just rotating and then reflecting across that line. And it will turn out that it's the same way in this case. We could rotate and then reflect, and that will be the same effect as a rotation or as a reflection across a different line. But we will put that off to the next video. The point of this video was just to give you an example of a particular reflection matrix. Now, before I end this, I want to sort of give you maybe a little bit of physical context, nothing, you know, like scary from theoretical physics or anything, but just more thinking about what the idea of reflection accomplishes. And so what I want to do is draw a person, and this is going to be a very poorly drawn person because I'm not going to make an effort to, well, let me make him have sort of a bigger torso. So, and his head is totally misshapen. He has a skinny neck. Totally deformed individual here. And it's just as well that he is, because we're going to do something to him that would not, well, it's not very humane, actually. Actually, maybe he looks kind of scary anyway, so should I give him a smile or a frown? I don't know. I could give him like a smile, but then I could give him like teeth or something. This is not someone who you'd be particularly eager to meet, I imagine. But he will serve for illustrative purposes. Okay, now, you know your heart's on your left side, right? At least most of you. So let's put his heart over here on his left side. All right, now, we're going to imagine that this guy really is two-dimensional. He lives totally in the plane. And if he lives totally in the plane, then there's no way I can't reflect like this physically. I can't peel him off the plane and flip him over, right? The best I could do is just rotate him around. So I could, you know, try and, this is going to be really bad, but try and just, so here he has his heart on his left side. I could rotate him around. So, you know, I can rotate him to where he's going this way. Right? He's still going to have his heart over on the left side. And then maybe now he's doing a handstand. And he's still going to have his heart on the left side. And then he'll come back here. So by rotating him, there's no way that you can change his heart over to the other side. However, suppose I could do a reflection. So I'm going to draw a coordinate system that goes like this. And so this is the x, this is the y. Suppose I could do a reflection. Well, then his heart would go over to the other side. See, his left hand would turn into his right hand would turn into his left hand, and so on. If you look at yourself in the mirror, say you're right-handed, go look at yourself in the mirror and pretend you're going to shake hands with yourself. You put out your right hand. Well, the person in the mirror is putting out their left hand towards you. So if you can accomplish a reflection, then you're doing something which is physically odd. It's an odd thing because it's something that, staying inside that space, as far as anybody knows, you wouldn't be able to do this. Now, there is a type of two-dimensional space in which you could move this guy around and his heart would come back on the other side. This is what's called a Mobius band. And this is what's called non-orientable. And it's a manifold. It's a two-dimensional manifold. It's non-orientable. And the way you can make one is if you take a piece of paper, you take a strip of paper like this, and you fold it around, but you fold it with a twist to where it's twisted over on itself like that. So it's not a full twist, it's a half twist. And so if you go around it once, you'll come back reversed. And then you have to go all the way around again to come back to where you're facing the same direction. So this is kind of a funny thing that happens with reflections. Now you could think about, rather than just, rotations and reflections in the plane, you could think about three-dimensional space. So you could think about O3, and you could think about SO3. And it would turn out that SO3 would just have rotations in three-dimensional space. Like I can rotate around this marker and everything. Whereas O3 would have reflections too. And so like if you go on a roller coaster, you could have elements of SO3 applied to you, but there's no way you can, as far as we know, in the way that space looks, there's no way you could have a reflection applied to you. Then your heart would be on the right side, or the right side. And it's worse than that because all your molecules in your body, well, most of them at least have a handedness to them. They're either right-handed or left-handed, all these complex organic molecules. So if you were reflected like that, you could no longer eat ordinary food. There's this thing, so there's this story called Through the Looking Glass, which is the sequel to Alice in Wonderland. Through the Looking Glass. And this, like I said, this comes from the Alice in Wonderland thing. It's the second book in that series. And he actually talks about if you go through the looking glass, if you could get to the other side of the mirror and you see food there, in that case he's talking about milk, would looking glass milk be good to drink? And the answer is no, it wouldn't be, because it has these molecules in it that are right-handed or left-handed, and if you went through, they change from one to the other, from right-handed to left-handed or vice versa, and they wouldn't match up with the molecules in your body properly. So there's a sense in which SO2, the special orthogonal group, which has just the rotations, is less weird in a way. It doesn't have as strange of transformational properties as what O2 does. O2 lets in some things that are kind of weird in terms of how you think about transforming things in general. So that's all I'm going to say for this video number 6. So let me put a check mark here. And in the next one, we'll talk about how to reflect across an arbitrary axis.